Today, we get to see the GNU Radio Workshop from the Microwave Update Conference of 2019, which actually took place in Louisville, Texas, a town just about 15 minutes away from me. So I recorded the whole conference except for one or two forums that they asked me not to record. And we're just now getting around to actually posting these because there was a lot of work on the back end to get the editing done. So I apologize for the delay, but this is like a Friday afternoon workshop that was setting up, installing, configuring, and running some practice tests with GNU Radio on a Windows operating system. So it's kind of long. Look in the description below for short links to different sections within the video, and I hope you enjoy it.
Shut up and sit down.
So today, what we're going to do is work on, and this is a workshop. So it's a chance for you to follow along with the slides and things like that, but also to actually try to physically get things working. So it's kind of like having somebody or your buddy there with you to work through it, so you're not left alone. And we're fortunate today to have Tom McDermott, N5EG, here to help us. And Tom is a guy that lived in the Dallas-Fort Worth area for many years, and he's done a lot of things in amateur radio, in TAPR, he's helped out in AMSAT, and many other projects for amateur radio, but he spent a great deal of time working with GNU Radio and has given talks in several occasions. There's a conference called the DCC, which is a ARRL and TAPR sponsored event, and he's given talks and sort of taught at those as well. And so he's very knowledgeable about it. He's also very knowledgeable about radios and how modulation works and ways to communicate at high speed. He worked in this professionally for many years also, and he's retired now and living in Oregon, in Medford, Oregon, and flew out to be with us today and work on this. We worked pretty hard to put this together for you and hope you enjoy it. And if there's something we can do as we go through it to make it more fun or help you learn more, we'd like to hear from you to do it. So I'm going to turn it over to Tom now.
Thank you, Bob. Okay, let's get started. The agenda today is we're going to install GNU Radio on Windows 64-bit operating system, and we've tested it on Windows 7 64-bit, Windows 10 64-bit, probably 7, 8, 9 different computers, and had good luck with it. Then we'll do a review of GNU Radio capabilities, how it works, and some important modules. And we're going to build a couple of projects and actually use the GNU Radio that we installed on the computer, make sure I understand how to use it, and then demonstrate a couple of applications. And then after the seminar, those who want to stick around, we'll probably talk a little bit more about radios and how to use things. So the exercises, we've got 4 exercises. One is to load an existing flow graph from a file and run it, and that will look at real signals and the spectra of real signals. And then we'll modify that flow graph to look at complex signals and the spectra of complex signals. It sounds scary, it's really easy. Then we'll go add noise and low-pass filtering, and we'll learn about the tap spectrum of a filter. And then we'll create a flow graph to play back an existing recording that was made a couple of months ago. And then if we can get it all working, and it's been a challenge this morning, we actually have a 2304 megahertz single sideband SDR demo, so we'll actually have a full duplex conversation on 2.34 gigahertz. So originally GNU Radio was a Linux project, and I think most folks are familiar with it on Linux. But last year, a maintainer built a Windows version of it. It was always theoretically possible, but challenging to do. And so he went ahead and built a pre-built Windows installer file and it's pretty easy to use. You don't really need to compile or build anything. You just install the file by putting the MSI installer on your computer and just double-clicking the install and standing back for a few minutes. That file is on the USB stick that you got for the workshop, and here's the URL for the latest version of the installer. What we're going to use in the workshop is not the latest version, and the reason is the latest version seems to have a bug in it, and it doesn't work correctly. The version that we have on the stick does work correctly, or at least on the 8 or 9 computers that we tested it. One of the limitations with the Windows version is that pre-built image only supports radios that the maintainer decided to support. So there are several very widely popular radios, but it's not easy to add new radios to that. In Linux, there is a fairly straightforward way to add support for new radios. There is not a straightforward way to do that in Windows. So let's look a little bit about what is GNU Radio. It's open source software. That means all the source code is available freely on the internet. It handles real-time digital signal processing. It will do simulation. It will do I/O with real radios. It handles all the buffer management. All of the real-time aspects you don't have to worry about. GNU Radio does all of that. It's based upon Python and C++. Python is used for the interconnection, for the graphics, for the management. You don't need to know Python. C++ is used for all the high-speed buffer functions, all the digital signal processing, all the I/O. You don't need to know C++. The installer takes care of setting all of this up for you, and it will wire up Python, it will wire up C++, and do it all automatically. The key concept in GNU Radio is a flow graph. And a flow graph is a Python program, and it's a text file that contains in Python all of the blocks, the GNU blocks, any radios that you might have, sources and sinks, the parameter values for all of those blocks, and what your flow graph will look like on your GUI display. What's wired to what modules, and what they look like. That's all in a flow graph. You don't need to know how to program, because there's another program with GNU Radio called GNU Radio Companion, or GRC. And it's a graphical GUI that takes care of doing all of the setup for you and displaying all of it. So you can basically bring up a flow graph which says what are all the signal processing blocks and what are the sources and sinks and how they're wired and what parameter values. It will compile that into a Python program and save the compiled program to disk and allow you to start and stop the flow graph, and it does the behind-the-scenes invocation of GNU Radio for you. So it lets you create and run digital signal processing without writing any code. It's all blocks. If you want a filter, you just grab a filter and drop it into your block and connect a wire to the input, a wire to the output, and tell it, is this a low-pass filter? Is it a high-pass filter? Where do I want the cutoff? And it will go figure out all the taps for you automatically behind the scenes. So you can do DSP without writing any software. It handles real-time buffering. And this is always the bugaboo in any DSP program, is that you have to have a lot of real fast behind-the-scenes code. GNU Radio, that's what it does. GNU Radio manages all the buffers, manages all the buffering. One thing that you have to make sure that you don't do is you can't have a loop in a flow graph. So things have to flow from sources through the flow graph to sinks, and you can't have any feedback in that process. There's a device called a throttle, and you need a throttle only if you don't have a real source of timing. And a real source of timing is a radio, or it's a Windows source like the microphone in your Windows PC, or a sink like the audio output for your PC. All of those are real sources of timing. If you don't have any of those, you're basically running a simulation rather than a real process. And then you need a throttle. So we'll see in the examples that we work through where we have throttles and where we don't have throttles. But all the throttle does is it keeps if you don't have any source of real timing, it tries to pull samples as fast as it can pull them from sources, tries to put them as fast as possible to sinks, and if you don't have something to slow down that process, your computer will lock up. But GNU Radio Companion will warn you if it thinks you need a throttle, and it can be in any data path. A few folks on the mailing list have had problems with the Windows audio sync. It can be a little goofy, and so every once in a while you may need a sync even though you have a real source of timing. So now we're going to install GNU Radio on your PC. You got a USB stick. Now's the time to plug the stick into your computer. And we're going to copy over all the files in the folder. Bob, do you remember what that folder is called? Like install? Okay, so drag that folder onto your desktop and copy all of those files over. It'll have the exercises, it'll have the installer for the program, it'll have the gigantic file where we recorded one of the contests. And put that on, and when you have that all copied over, you can then eject your stick. And the reason for doing this is if you mess up something, you'll have the original copy on the stick, and we can go back and retrieve it from the stick if we need to. So everybody found the folder okay? You copied over the desktop? We all done? Is anybody awake? Okay, eject the USB stick and pull it out, and you will find in that folder an installer for GNU Radio, and it is what's called an MSI file, which is the Microsoft installer file. And when you get that file pointed to, go ahead and double-click that file, and that will start the installation process for GNU Radio on your computer. Everybody find it? That's it. That's it. Okay. Anyone need help finding the installer file? Okay. Go ahead and click it. It'll take a couple minutes to install. And what the install process does is it will load Python onto your computer. It will load all of the GNU Radio modules, and then it will build a complete environment, and then it will give you an icon for launching GNU Radio Companion. And depending on if you have Windows 7 or if you have Windows 10, where the icon is, gets placed a little bit differently. Yeah, if you have problems, raise your hand and we'll send someone over to help out. Yes? I think it uses 2.7. GNU Radio, there's a version 3.8 that's out. There's no Windows installer for 3.8 yet. 3.8 uses Python 3.6, I think. However, it's still being debugged, and the Windows maintain it changes a lot of the plumbing behind the scenes, and so building a new Windows installer is going to be a somewhat involved process for the maintainer to bring up. The install also installs the online help, or the manual for GNU Radio. There's no icon, but it's an HTML file, and on the USB stick there's a copy of these slides, as well as they're in the booklet that you got for the class. And this URL, C program files, GNU Radio 3.7, share doc, and 3.7, and XX and YY are the version number. It's probably .14 something /HTML/index. That will bring up help for GNU Radio. So we don't need to do that now, but if you need to look at help, you'll find it there. So then, when it's done, you have to bring up GNU Radio by launching the GNU Radio program. So on this laptop, I put the icon in the start menu for Windows 10. It says GNU Radio Companion. You can put that anywhere you want. You can have it on your desktop. You can have it in the start menu. And Windows 7, of course, doesn't have this kind of a start menu, but it'll be there. So when you're done installing and the installer completes, go ahead and click on this GNU Radio Companion icon. And what it'll do is bring up a window, and then it will start it like this. So you should get something that looks like this. It'll probably bring up an empty window that looks something like this. So has everyone gotten through the install process and successfully started it? Not yet? Okay. We found that Windows 10 computers tend to do the install about 2 or 3 times faster than Windows 7, and that may be because the Windows 7 computers tend to be older computers for most folks, and so they tend to be a little bit slower, so the install takes a little bit longer. So if you run into any kind of problems, just put up your hand and we'll have someone come around and try and help you get going here. So when you click the icon, it's actually going up, setting up the environment variables, bringing up the version of Python, and then once it does all of that, it will launch GNU Radio Companion. So let me ask the question a different way. Has anyone gotten this far? Okay, good. We've got a few. Yes, yeah, you want to launch GNU Radio Companion. It's usually abbreviated GRC. Yes. Yeah, GNU Radio, if you want to use it for good performance, it takes a little bit of computing horsepower to run. There's you should be able to do all the exercises here without a lot of performance, since they're all file-based or simulation-based. If you run it with a real radio, then you may need a higher performance computer. Okay, when you get this window up, you'll see a window. There's a bar of icons across the top. And we have a canvas here. We have a list of blocks. We have a console. And we have a window that lists some of the variables that we have going in the session. So it has the similar kind of icons that most Windows programs have. You have a new, which will create a new flow graph. We have an open, which looks like a folder, and it's got a drop down so you can open recent flow graphs, or you can tell it to go to disk and find a particular place on disk where there's a flow graph. There's a floppy disk here, so you click that, it'll save the flow graph. If you haven't named it yet, it'll ask you where you want to save the flow graph. And then there's two other buttons, the compile button and the run button. What the compile button does is once you've put all of your blocks onto the canvas and you've wired them up, it will create the GNU radio flow graph from the drawing that you have on the screen. And if you click the run button, it will then actually run that flow graph. If you haven't compiled yet and you just click run, it'll compile it first and then it'll run it. So it's smart. And then there's the magnifying glass here, which is the block search. And it will open up a little search window over the blocks where if you know the name or the first few characters of the block, you can type it in and it'll bring the candidate block names up into the blocks list here. Down here is the console. It'll tell you where it thinks the blocks are, and it'll give you the version number 3.7, whatever, 13.4 or 14. Something that you have. Okay, is everybody here? Are we still trying to build and get going yet? We have anyone waiting, or everybody get to this point? Okay. Okay, after it's installed, you should find an icon called GNU Radio Companion, and it'll either, depends on if you have Windows 7 or Windows 10. Yeah, it may be in the Start menu. Okay, so this is the screen that you get. This has already got the first flow graph loaded. So now we're going to do exercise number 1. And you should have GNU Radio Companion up and running. And there is a file supplied on the USB stick, which it should be on the folder that you copied onto your desktop, called exercise_1. And so using the open block here, we're going to open and find exercise number 1 and open exercise_1.grc. So has everyone found where the exercises are on your computer? It's in one of the folders in the MUD 2019 folder that you copied onto your desktop. Has everyone found it? Is anyone trying to find that exercise? Okay, Jenner, can you help? Stick up your hand here. Stick up your hand and Jenner will come help. We have one more. We have a couple folks who still haven't been able to find the exercise. Okay, if you have the exercise loaded, go ahead and click the Run button right here, and it should bring up a GUI where you can see what the exercise is doing. Okay, very good. So what are we seeing on this exercise? You should see a spectrum analyzer display. And the device that you're seeing is called a frequency sink, and it's basically just a spectrum analyzer. In the flow graph, we have a signal source, a throttle, because we don't have any source of real timing. We're just simulating a source. We have a throttle to slow it down, and we're displaying the output. Yeah, this should be exercise 1, should look like this. So we have a signal source, we have a float to complex, we have a throttle, and we have a frequency sink. Okay? And the orange boxes are real signals. The blue boxes are complex signals. So when we take a signal source putting out a real sine wave, and we do a float to complex conversion, we add in the real part, and we don't have anything hooked up to the imaginary part, so it automatically inserts zeros for you. So we have a signal that's formatted complex, but the imaginary parts are all zeros, so you just have the real signal. And that's so we can then run it through the rest of the samples to complex, and we can go to a frequency sink. I don't know if I have, let me bring up that flow graph and run it at the same time. So let's file, open. And you should get something that looks like this. So what we can do now is let's yeah, it's this thing right here. I have the X term error. So on this display, okay, have we got to this display here? Okay, what are we seeing? We're seeing a spectrum, and the spectrum display goes from minus 16 kilohertz through 0 to plus 16 kilohertz. Complex numbers can have negative frequencies as well as positive frequencies. We can't do that with real numbers, but we can do that with complex numbers. And we see two spikes in the display here. We see the left-hand spike at minus 4 kilohertz and the right-hand spike at plus 4 kilohertz. What does that tell us? Well, if we go back and look at the flow graph, the signal source is programmed to 4 kilohertz. So there's a parameter in that block that we set to 4. And when we convert it to a floating point number and we look at it, to a complex number, and we look at it as a complex, we get two spectral lines, minus 4 and plus 4. And the reason is that if we have a complex number that doesn't have any imaginary part, in fact, we have two simultaneous frequencies coming out of that converter block. So the next thing we want to do, let me look at my slides and see if I can remember where I was. We have in the block called a source, and that source is a simulated source. It basically is set to stream a sine wave into your flow graph. A source is anything that streams samples into your flow graph. So a source from nothing creates samples and then streams those samples into your flow graph. A sink is something that removes samples from your flow graph. So the spectrum analyzer display is a sink. It's taking samples out of your flow graph and displaying them on the screen. And then there are general blocks which receive samples, do some kind of transformation on them, or maybe it's a throttle. There's a bunch of things it can do, and then outputs them. And an example of general blocks is the throttle that you have, or a low-pass filter, FM demodulator, delay block. There's a lot of different kinds of general blocks. The signal formats are color-coded. Blue is complex single precision. So there's an I component and a Q component packed into that blue block. Orange is single precision, 32-bit floating point. And there's a bunch of others. You'll find a help up at the top of your flow graph, and it'll pop open a little legend, and it'll tell you what all the colors mean and what kind of types they are. There's a type converter block, which we've seen in exercise 1, and there's a complex to float, which has one blue input and 2 orange outputs. There's a float to complex, which has 2 oranges to a blue. So complex versus real. A complex signal contains both an in-phase signal, which is the I component, and a quadrature phase, which is the Q component. A real is a single floating point number per sample, and complex is a pair of floating point numbers per sample. And GNU radio keeps the complex number parts together. So it calls it a single sample, but it really has an I floating point and a Q floating point. A complex number describes a vector on the complex plane. If that vector rotates counterclockwise, that is considered to be a positive frequency. If that vector rotates counterclockwise, it's considered to be negative frequency. A real number, since there is no I part, can't rotate. It just goes back and forth on the complex. And you can show that a back and forth line is the sum of a positive component added to a negative component. And so if you have the two vectors going around at the same time, the I parts cancel out, and the Q parts cancel out, and you're just left with the I part. That's why you see a negative frequency plus a positive frequency, is because the Q components cancel out. So this is this vector that we're talking about. We have a real and an imaginary component. And any single frequency is the sum of the cosine, which is doing this bit, and I, the imaginary operator. Sometimes in engineering we use J instead of I. But mathematically they're the same thing. And that's this component here. And so it turns out that a single frequency sinusoid is this vector, and it just draws the unit circle on the complex plane, and that's a sine wave. And that's a single frequency. If it's going counterclockwise once a second, that's positive 1 hertz, and if it's counterclockwise once a second, that's negative 1 hertz. You can also express it as a e to the I omega t, exactly the same thing as the amplitude times the cosine plus I times the sine. And so a sine wave is just a unit trip around. Okay, so let's talk. Each block has to know about the sample rate of the samples coming into the block and the samples going out of the block. And every block, or almost every block, there's some blocks that don't need to know, will have a variable called sample rate. And in that block, you tell it what the sample rate is. GNU radio has a shorthand. There's a variable called SAMP underscore rate, samp rate. And most times, if you construct a new block, it'll automatically put the variable samp rate into the variable rate, so it'll automatically populate it for you. So sometimes you may change the sample rate of a signal going through the block. Not often, but there's a few times. So one of the blocks that changes the sample rate is called decimation. And decimation is a process to reduce the sample rate. So if you have a radio that's producing 1 million samples per second, but the information's only audio bandwidth is only 10 kilohertz wide, you don't need to process 1 million samples per second. And you can run that radio into the decimation block, and tell it, reduce the sample rate of the stream, and it will go back and reduce it. So one of the tips in building flow graphs is to decimate the samples close to the source if you can, and then put them back to a faster sample rate where you may have a transmitter that needs it, and that process is called interpolation. So we're going to go to exercise number 2, and instead of loading it from the exercises, we're going to modify the file that we currently have on disk. And so let's go to the GNU radio window, and we're going to change the signal source and get rid of this block, and we're going to make this everything complex, no floating point numbers. So if we want to change the format of a signal, we can go to the signal source, select it with one click, and then double click, and it'll bring up the block for the signal source. And here's the block for that source, and you can see the sample rate is set to samp rate, and we have it set to 4 kilohertz. The output type is float, and what we need to do is to go change float to complex, and that hit OK. And you'll now notice that what we have is an arrow with a red tip on it. And what that tells us is that we're producing a complex, and we're trying to sync it into a real, and that's a type mismatch. We can't do that. So we'll go to the float to complex, and we'll click delete, and that will get rid of the block, and then we'll go wire from out of the signal source to the input of the throttle. And now we have all blue all the way through. So we have a complex signal coming out of the source, going complex into the throttle, and complex going out to the sink. So before you click run, we're going to save as, and we're going to change the name. So you can call the name, for example, exercise 1C for complex, and then save it. And that way we won't overwrite exercise 1. And that's one of the reasons that we pulled the USB stick out, is it's easy to accidentally overwrite the exercises, so you still have them on the USB stick if you accidentally did that. Pardon? Okay, you just double click the box and it'll bring up the menu. Okay, yes, to put the line between them, if you select the line and hit delete, that erases the line. And now you notice the blocks have red names. The red names mean something's wrong with the block. That doesn't have anything. So you click one end of the wire, you take the mouse over and click the other end, and it'll drop a wire between them. So once we put a wire here, we can now run this flow graph. And we click run. And what we should get is a spectrum display that looks like this. And what that shows is, because we are now running a complex source and complex samples, we lost this negative frequency component over here, and we just have a positive 4 kilohertz signal. So that shows that the spectrum of a complex signal is single-sided, where the spectrum of a real signal is double-sided. It's got both positive and negative frequencies in a real signal. If we zoom way down here, we have some buttons on our spectrum display over here, and we can go zoom down into the display. So there's what's called Y range, and that allows us, if we click the plus on the Y range over here, in the control panel, we can go bring in, and so now we can see that we have the Y signal. And if we look down here, we notice all the grass down here. And the reason is because that's about 150 or 160 dB down, and we're now down into the precision of a single precision floating point number. And so we're actually looking at the artifacts of having just a 32-bit floating point number. And so for most practical purposes, we can kind of ignore that noise that's 150 or 160 dB down. Yeah. So you can stop your flow graph any of a couple of ways. You can click the red stop sign here, as Bob talked about, or you can click the close on the spectrum display. So if you have this display up and you just click the close box up here in the corner, the X up here, either of those two ways will stop the running flow graph. Okay, did we all get through this exercise? So now we can make some modifications to the frequency sync. GNU Radio has a bunch of different pieces of test equipment built right into the program. There's an oscilloscope, what's called a constellation. There's the frequency sync. So let's stop the flow graph that's running and double click on the frequency sync, and you'll bring up this block. And this block is a parameter block that lets you control the characteristics of that frequency sync. And so the first thing we notice is that it's type complex. And we didn't give it a name, but we could have named it. We have a fast Fourier transform size, and we can put in a power of 2 there, 2048, 1024, 512, whatever we want. And that'll set the resolution in terms of number of bins that we get in the display. The window type will allow rolling off the samples at the end of the window. We won't talk about that, except if you change it to rectangular and run it, go ahead and change to rectangular, OK, and run exercise 2. And we go change the Y range. You'll get something that looks like this. And there, what we're getting is some spectral artifacts that have to do with the fact that we have a sine wave that's not exactly an integral number of the number of displays. And if we change we can also change that here in the FFT display. So we got a couple different ways to change that. A couple of other things we can do. We can change the number of channels. Right now we're on 1 channel, but we can change it to 2 channels. So we can have a 2-input spectrum display, and we can run 2 different signals into the block, and it will show the 2 signals at the same time. That's very handy. So we have the data format type. We have the number of inputs on the General tab. And if we go to the Configuration tab, we can select this thing called the Control Panel. And the control panel is what gives you the ability to, that's what's the, this is the control panel over here, so that will turn that on and off. So we've simulated a couple of real and complex signals. Let's load exercise number 3. So I can go to File, Open, and find exercise 3. And it should look something like this. Here we're going to get a little fancier. We have a signal source, and we're going to add a noise source. So one of the signal generator types in GNU Radio is a broadband noise source. So what we're going to do here is we're going to take the noise source and we're going to run it through a new block, a low-pass filter. And all of these are complex types, so they're all single-sided spectrum. And we're going to add this noise to the signal source. So we'll have a signal source add, and a noise source. We're going to filter the noise source, and we're going to add. Now the low-pass filter is strictly low pass, and so it's got complex in and out. And what happens when we run this spectrum? You get a display that looks something like this. So here we have our plus 4 kilohertz signal, and we have the noise from the noise source, which we filtered, starting around 5 kilohertz. We've rolled it off. So let's go and play with this control marked average up here. And so if we slide the average down to the left, what are we doing? We're averaging that spectrum display. So we see the noise kind of decrease. And we can go turn on the grid. So if we click the grid checkbox, we get a nice grid display so we can actually see the numbers. And we'll get a grid line here on 0, another grid line on 5 kilohertz. So what is this low-pass filter doing? It turns out that the taps for the low-pass filter are just low-pass. We're used to low-pass in the real domain, so when we say something has a 5 kilohertz low-pass, we know that it's 5 kilohertz or less. But a low-pass in the complex domain, low-pass is everything from minus 5 kilohertz to plus 5 kilohertz. And so a low-pass filter, and indeed something called the Nyquist criteria, applies to both positive and negative frequencies. So we should have something like this where our noise has both positive and negative components, and we're going just through, and we see just the one complex source. And we have a number of different types of filters available to us. We're not going to go into those right now. And we're going to kind of go back and go through a little bit of theory here. Yes? Yep. Yeah, so what these are the stop band responses from the particular filter that we've implemented. So if we look at the filter type, we have the cutoff frequency set at 5 kilohertz, a transition band of 2, and we have a window here called a Hamming window. And a Hamming window is the kind of low-pass filter response that we have. And a Hamming filter has minima in the stop band, and you can see those minima on that display, and that's exactly what you're seeing. So if we want to, we can change that from a Hamming, let's say, to a Blackman filter. And we click OK. Let's stop the flow graph and change it from Blackman to, let's say, Hamming. and then restart it. And now let's go average this a little bit. And you'll see actually that the filter shape changes a little bit where some of those things are. So you have various different filter functions available to you. We can pick a rectangular and we'll get some different things. But that's a good observation. You can actually see what your low-pass filter is doing. When you run noise into a low-pass filter because it's broadband noise, and then filter it, you can actually observe what's happening to the filter response function. So let's pick rectangular and run it. And here we can see that rectangular is in general not a real good low-pass filter. So you can see it's still low-passing, and then you've got some bigger. You basically get the first lobe here is down about. Let me turn on the grid. It should be 13 dB down. No, it's 20. It's about 20-something dB down. So a rectangular filter just chops off any spectral components right at the edge of the passband, and you can see that that's in general a bad way to build a low-pass filter. There are other filters which will actually let you use complex tap spectrum instead of real value tap spectrum. But real is what you get in the default low-pass filter. So there are other low-pass filter types available here. So the low-pass filter gives you several common filter shapes, and it's got a couple of other variables here. We haven't yet talked about decimation, but we will talk about that a little bit later. And it's 4 o'clock. Do we want to take a break now, Bob, or we want to keep on going? Okay, is everyone following along? Have we lost anybody completely? Everyone working okay? All right. So this is that low-pass filter block, and you can program into it the type of filter, and we'll talk about the sample rate here. So it provides common filter shapes. There's a lot of them built in. There's band pass, low pass, and high pass filters built into GNU Radio. You don't have to design them yourself. You just grab one and drop it in. So in exercise 3, note the spectral response. So we can say that a complex sinusoid is just one frequency component. It's not two, where a real signal is two. What does negative frequency mean? It just means that the vector is rotating the opposite direction. And if we actually want to build a receiver and tune, we can listen to just one or the other of those things. You can consider one of those signals as an upper sideband and the other signal as a lower sideband, but they're just two different discrete frequencies, and they're actually separately tunable. Some of the key modules: low-pass filters, band-pass filters, high-pass. There's pre-made filters. You can build custom filters, and you don't actually have to write any software because you can define your own taps if you want to. So in any filter, any digital filter, you define the transfer function of the filter by the taps that you use. And the taps are just a bunch of constants that define the response of the filter. GNU Radio includes a filter designer GUI, and it will automatically create taps for you if you want to build a custom filter. But if you just want to use the normal low pass, high pass, or band pass filters, you don't have to design taps. You can just use the filters that are already built in a GNU radio, and you don't have to worry about that. I would say 99% of the time I just use the built-in filters. It's very, very rare when you need a special custom filter function. If you're trying to build a filter that has a very, very low cutoff frequency, for example, if you're running something at 48 kilosamples per second and you want to filter to 5 or 10 hertz, that filter is going to have a lot of taps in it. And all of those taps mean that it takes a lot of computational effort to go through all of the multiplies that it takes. So if you try to build something that's really, really low in frequency, your PC may get sluggish. As we saw, if we have real taps, for example, the default low-pass filter, even though the signal in and out is complex, the taps are real. And that means the spectrum of the low-pass filter includes both negative and positive frequencies, because the spectrum of the taps, being real taps, is a double-sided spectrum. And so if we want a filter that's only positive or only negative, then we need complex taps, because the spectrum of the taps is then single-sided. So complex taps gives you a single-sided response, real taps gives you a double-sided response. Some of the other modules, we used the add module in exercise 3, where we added the noise to the signal. So adding just sums the two signals, and it does what you think it would do. If you have two signals, you get the sum of the two outputs. Multiply multiplies two signals sample by sample. We haven't used the multiply yet, but we will. And a multiply is a mixer. So in analog, we're used to mixers, and what do mixers do? They produce sum and difference frequencies. In the complex world, if the reason they produce sum and difference is because we use real numbers, and a real signal, a hardware mixer or hardware multiplier, where you feed in an electrical signal, there's no I and Q component, it's just one component. And so that mixer, electrical mixer, is actually interpreting that as both a positive and a negative frequency. So when you interject an LO, it's a positive and a negative, and when you inject a signal, it's a positive and negative. And that means that the mixer produces a sum and a difference frequency. And when you look at the output, you'll see a positive sum and difference and a negative sum and difference. And so a hardware mixer actually produces 4 components. But because you're looking at an electrical signal, you can't see negative frequencies with one wire. And so you only see the 2. And so a real mixer produces sum and difference. A complex mixer has just a single frequency in on the LO and a single frequency on the signal, and it produces only the sum signal. And so in math, when you have complex signals and you multiply them, you get a mixer that only produces one component. It doesn't produce the sum and the difference. It just produces the sum. And so a mixer is basically a frequency shifter. And you can shift a signal anywhere up or down you want simply by multiplying it by a sine wave. And as long as all the signals are complex in and out, all it's doing is sliding the frequency back or forth. And so by changing the LO, you can change the signal going through the mixer. And so complex mixers are very much friendlier to use than an electrical mixer, because you never have to worry about the sum and the difference. You just get the sum. There's converters that convert float to complex. We saw one of those in exercise 2, where the block had 2 orange inputs and 1 blue output, and that block is just merging the I and the Q signals into an output. We didn't hook anything up to the I, and so that block said, there's nothing wired up, so I'm going to insert zeros, because there's nothing there. But if we'd had another signal source and hooked it up, it would have inserted those instead. There's many, many blocks, and you can explore those on your own. This is the Filter Designer tool. If you go to the Tools, Filter Design menu in GNU Radio Companion, it'll pop open this window. And this is the window that lets you design your own filters. You don't need to use it, but if you want to, you can. It creates a filter taps file, and then you can use the generic filter function in GNU Radio, and it'll ask you what taps do you want, and you just point it to the file that you created using this tool. And now you have your custom filter. This tool will give you pole zero plots, it'll give you band diagrams, and I'll let you explore that on your own, but any kind of classical filter that you design from text, you can visualize with the tool. It's very powerful. If you try to build your 2 Hertz filter, it's going to try to create thousands of samples, and your computer is probably going to go to sleep for a long time. So try not to build real ultra narrow filters with this, or you'll find that you generate huge files and there's an intense amount of computation going on in the PC. So you tell it the sample rate you want, the gain of the filter, the pass band, the stop band, the attenuation, and you can plot the impulse response, the step response. You've got all kinds of options for visualizing the filter, and just play with it, try it out, see what kind of filters you get, and then if you want, you can actually build a flow graph, simulate it, see if it does what you want to do. The next topic is sample rate. One of the key things that you have to worry about in a flow graph is to keep track of the sample rate throughout your flow graph. And I'll underline, if you don't, bad things will happen. Nothing will be damaged, it just won't work, and it'll drive you crazy trying to figure out what's going on. In digital signal processing, there are 2 functions that change sample rates. One is called decimation, and the other is called interpolation. And decimation allows you to reduce the sample rate of a stream. And it's pretty easy. For example, if we have a 1 kilohertz sine wave and it's sampled at 100 kilosamples per second, and we don't really need that fast of a sample rate because the frequency is pretty low. So we're getting real fine granularity on the samples. We could reduce that sample rate without losing much information. And the way that we do that in signal processing is, let's say that we wanted to reduce the sample rate to 10 kilosamples a second from 100. The Nyquist bandwidth, we all remember Nyquist, right? We have to reduce the bandwidth to half of the sample rate, right? If we don't, then we get aliasing products. So at 100 kilosamples per second, the Nyquist bandwidth is 50 kilohertz. And with a complex number, that's minus 50 through 0 to plus 50 kilohertz. That's the Nyquist frequency band of a 100 kilosample per second stream. Let's say that we want to decimate that to 10 kilosamples per second. Well, what's the Nyquist rate of a 10 kilosample per second stream? It's 5 kilohertz, minus 5 to plus 5. So to decimate, what you do is you first filter the incoming signal. So we have this 100 kilosample signal coming in. We'll run it through a 5 kilohertz low pass filter, and then we'll throw away 9 samples, keep 1 sample. Throw away 9 samples, keep a sample. Throw away 9, keep. So the output rate is now 1/10 of the input rate, and we can see everything in the minus 5 to plus 5 range that was originally in the 100 kilosample per second file. So decimation is the process of reducing the sample rate, but if we don't filter first, we will get garbage. And where that garbage comes from is aliasing. For example, if there was a signal at 20 kilohertz and we didn't low pass filter, then we would get the signal around 20 kilohertz would appear folded down at 0 in the output stream, and every harmonic of 10 kilohertz would get folded down into baseband. And that's why you have to sample to the Nyquist rate, is to avoid that. The opposite process is called interpolation. And interpolation lets us increase the sample rate. If we have a 1 kilohertz signal that's sampled at 10 kilosamples per second, and we need to create a 100 kilosample per second signal, then what we do is for each sample that comes in, we'll take the sample from the input stream and copy it to the output, and then we'll insert 9 zero samples. Then we'll take the next sample from the input stream, then we'll insert 9 more zeros. So sample, 9 zeros. Next sample, 9 time sample zeros. So sample, zeros, sample, zeros. Then we low pass filter that signal to 5 kilohertz because the original information coming in was only valid from -5 to +5 because it was a 10 kilosample per second stream. So we then, after interpolation, we then low pass filter to plus and minus 5 kilohertz. And we now have that signal, except it's clocking out at 100 kilosamples per second. And we can pick ratios. So we could interpolate by 10 and decimate by 9. And then we end up with a sample rate that's 10/9 of the input sample rate. So all of those things are due. That's how we change sample rates in any kind of a digital signal process.
Take a look at your book on the front of it and the back of it. That's graphically illustrated on the cover of the book, okay? It's an important concept.
So there's a default variable when you build your flow graph, and you can change the name if you don't like what GNU Radio picked. It's called samp_rate. And it will, the very first time you create one, it'll set it to 32,000, which is the sample rate it wants to run the flow graph. And you'll probably want to change that value first thing. If you're going to use the audio sound card in your computer, it probably runs at 48K, or maybe it runs at 96K. So you might want to change that variable to 48,000 or to 96,000. So you just double click that variable blocks, just like any of the other blocks, and you'll see the number 32,000 in it, and you just type it and change it. Now, if you're going to change the sample rate, you have to make sure that each block has the value sample rate in it corresponding to the actual sample rate that the block is seeing. And that's the connotation of otherwise bad things happen. So if we can do that a couple of ways. We can just hard type in, let's say that let's bring up a flow graph here. And so here's our variable. We'll double click it, and it says 32,000, because that's the default when we create a new one. And let's just go ahead and change that to 48,000. And we'll create a signal source. So we'll go to source, and we have waveform generator, and let's pick a signal source here. And notice the sample rate on it now says 48K. So if we go look into it, the reason is because when you select a new signal source, it automatically populates the variable samp rate into its sample rate. And if that's what you want, fine. And if it's not what you want, change it. You can put any valid Python expression into a numeric block. So you could put the number 48,000, or you could put the number samp rate times 10. So samp rate times 10 might be a useful, for example, if you have an interpolation somewhere, and you happen to interpolate by 10, and the inputs to the interpolator is running at samp rate, then the output's going to be running at 10 times samp rate. So if you just type in samp rate times 10 in the block that's going to consume those samples, then you never have to worry about it because it'll automatically compute the right number. And your flow graph, if you change the variable samp rate, then the blocks that depend on it will also automatically change. So now we're going to go add and so the block that does it is called rational resampler. So we'll bring up this rational resampler block. And you can see it's got a floating point input and output, so we'll wire those together. And we'll tell it, let's interpolate by the factor of 2. And let's decimate by 1, which means it doesn't do any decimation. And we're going to leave this block taps empty. GNU Radio, when you build the rational resampler, if you don't put any taps or any fractional bandwidth in, it'll automatically construct a Nyquist filter for you and populate it. So you don't need to worry about it. Just will build the correct Nyquist filter for you automatically. It'll look at interpolation, it'll look at decimation, it'll compute the right Nyquist filter, it'll build it, and you're all done. So we're now done. So now we have a block that we're streaming in samples at 48,000 samples per second, and we're streaming out samples at 96,000 samples per second. So let's go consume those samples. And let's consume them with a sink. A sink is a thing that consumes samples. So we'll input a sink, and let's use an audio sink here. Now notice the audio sink defaults to samp rate. That's 48,000. We can't wire the rational resampler to the audio sink because the sample rates don't match. The interpolator here creates 96,000 samples a second, and the audio sink would only consume 48. So let's multiply by 2. So samp rate times 2 is a Python expression. And now it's going to run, it tells you here it's going to run at 96,000 samples per second. Now an audio card in your computer can't do anything with complex samples because it eventually goes to a wire. Yes, sir? Yes. Oh, okay. See, there's a magnifying glass. Click the magnifying glass, and then you can type in a first couple of letters, and it will give you a listing of what it thinks is close to what you want. And then you can either double click it, or you can click it and drag it down, either way. And once it's on your flow graph, single click it to highlight it, and then hit the delete key and it's gone. Okay. Okay. Can't see these blocks here? Okay. Yeah, okay. So this is what's called a rational resampler, and this one's called audio sync. And so I got to audio sync. The first one, that's a signal source. They're blocks. Yes, variable is this parameter, and then you have another block called options. I'm sorry? Yes, so yeah, to do that, you double click the block. Is that the question? Ah, okay. Yeah, the type font's a little slow. I don't think I can magnify this on screen. So what I entered is 2 for interpolation, 1 for decimation, and I left everything else unchanged. It is the sound card in your computer, and it will come out the audio output of your computer. So if you have a speaker on your computer, it will come out. So it's whatever the audio card is in your computer. The audio source is the microphone in your computer, or the line into the sound card, whatever sound device you happen to have plugged into the computer. So now we have one problem. We can't wire the rational resampler over to the audio sync because we have a type mismatch. We got a complex number here, and we have a real number there. So we get this red arrow, and the red arrow means isn't going to run. And if we try to compile it, we get this little icon with the bar in it, and it's telling us it's not going to compile. So let's select the line and then hit the delete key. And now we have to convert complex to float. So we'll go up and let's search for, in the search box all the way over here, we'll type complex, and you'll see it suggests type converters. So let's go down to that second one, complex to float, and double click it. And now we have this block, complex to float. And it does just about what you think it does. So we'll wire the input, and we'll choose either one of the outputs. Let's take the reel to the audio sync, and all the red bars are gone. So what we're doing is taking the complex number, we're going to throw away the imaginary part, and we're just going to keep the real part. Why? Because the sound in your computer is just a wire feeding a speaker. That's an electrical signal, and it can only be a real value. Any wire is only a real valued signal. And so the audio sync is equivalently only capable of hearing a real signal. And if we run this, we should get audio. And it wants a name, so we will give this, we'll call it audio.grc. Put it on the desktop, save it. Okay, now we can hear the 1 kilohertz audio coming out of our signal source. You notice we didn't need a throttle. And the reason that we don't need a throttle, let me stop this here, it's pretty annoying. Okay. Okay. You click one box and then take your mouse and click the other box and it will connect them. Nope. I left that last one suspended and running in the background, so I killed it. We actually used that earlier this morning to test that the audio sound worked. So what we've successfully done here is we've created a kilohertz, we've changed it from 48K sample rate to 96, and then we've output that to the speaker in the computer. And in fact, there's a lot of things you can do. So if we want to, for example, build a mixer, let's delete the line. Let's go search for multiplier, and it'll suggest multiplies. Let's go pick the multiply block over here, multiply, and we'll double click that, and we have a multiply, and we'll and what can we do with multiply? We can do a lot of things with multiply. If we put in a constant to multiply, say 1, what does it do? Well, it doesn't do anything at all. It just multiplies every sample by 1. What if we put in a value 2? It's going to multiply every sample by 2. In other words, 6 dB gain. Or we could put in a half, and it would multiply every sample by half, 6 dB of attenuation. So if we just put a constant into the input, we have a level control. If we put a sine wave into the input, we have a mixer. Excellent question. So one of the next blocks that we find very useful, let's go up here to the blocks and type the word GUI. Okay? And under GUI, you'll see QT. I'll give you a little advice here. There's two kinds of interfaces, WX and QT. WX has been deprecated and is going away. And so my recommendation is just use QT GUI. Don't use WX. The flow graphs default to QT GUI. And in the next version of GNU Radio, WX won't exist. So stick with QT and then you won't have to learn it twice. And let's go pick a block called slider. And we'll drag the slider on. And let's open the slider. And it's got an ID and a label and some default values, minimum and maximum. Yes, sir. My mistake, thank you. Okay. Let me delete that. And it's called range in QT, of course. So range, thank you for pointing that out. I would have had a miserably failing flow graph here in about 5 seconds, so saves time. So let's double click the QT GUI range. And what it's going to give us is a slider object. And as we slide it on the GUI, it'll change the value of the variable. So while our flow graph is running, we can change the number. Now we need to give it a name. It picks a name that's very unfriendly. And let's just call this S1 for slider number 1. And we'll leave the label empty for now. Let's change the default value to 0.5. The start is 0, the stop is 1. And it's currently set to 50, 0, and 100. And let's set the step to 0.1. And click OK. Now we have a complex multiplier, and the range gives us a real value. It's called a float. And so we're going to need a type converter. And so we'll just say float to complex. And it won't let me do what I want to do here. I should have thought this through. So if you do Control-C, Control-V, you can copy a block that you already have. And if you hit up arrow, down arrow while a block is selected, we can scroll through all these variable types here on the block. So let's set it to a float. Tell you what, let's make this simpler. So now we have two signal sources, and we're going to multiply them together. They're both at 48K. One of them is set to a kilohertz, and the second one, since we copied it, is a kilohertz, and we're going to change that. So we'll open it. And where it says frequency here, in the middle, it says 1,000 because we just copied the existing block. And we're going to change that to S1. And so what it's going to do is put the value of slider number 1 here that we called S1, and it's going to set the frequency of that source to S1. And now what happens if we run this block? We get this slider object here, and we can slide this back and forth. So let's go, so you can just take the mouse and grab it. And I got the wrong range. So we want this in kilohertz. So we'll say S1 times about 5,000. And so our slider goes from 0 to 1, and if we multiply it by 5,000, it'll now go from 0 to 5,000 in this block. Okay, S1, when we instantiated the GUI range, I typed S1 into the ID, and now all the blocks in the flow graph can refer to that variable by its name S1. Now as we move the slider, we should be able to hear it change frequency. Yeah, that was me. So what did we do? We took a 1 kilohertz signal and we mixed it with a 0 to 5 kilohertz signal. And since they're both complex numbers, the multiplier here just shifted. So when this is 0.1 on the slider, we multiplied it by 5,000. So S1 times 5,000 in the frequency. So the lowest value here at 0.1 is 0.1 times 5,000 or 500. So a kilohertz mixed up by 500 hertz gives us 1.5 kilohertz out. Okay, the slider is we got this control QT GUI. Okay, and drag it onto the screen. Okay, and then when you click it, give it a label ID. Okay, when you run the flow graph, okay, and so notice that this multiplier is summing those two signals, right? The frequency out is the sum of the two frequencies in. Because they're complex numbers, it's always the sum. So the question is, how do I get the difference frequency? And the answer is there's two ways to do it. One is to give it a negative frequency. So we just type we can set the frequency and we can just type a minus sign in front of the frequency, and then it'll put out minus 5,000. And so for example, if we set it to 500 hertz, then it'll put out 1,000 minus 500 or 500 hertz. There's another way to do it if you don't have access to the minus sign, and that's a block called complex conjugate. When you take the complex conjugate of a number, you flip the sign of the frequency. And so you can find a complex conjugate block and just use that, or you can use the minus sign in the frequency, either way that you want. So the complex multiply produces a frequency shift. It doesn't produce sum and differences, it only produces the sum. real multiplies do produce the sum and the difference frequencies. A negative frequency carrier is used to down convert, and you can do that by either entering the frequency as a negative number or taking the complex conjugate of a frequency, and the complex conjugate has the effect of flipping the sign on the frequency. So now we get to exercise number 4. This one we're going to load a pre-existing flow graph because it's a bit more complicated. And what it does is flow graph number 4. About 2 months ago, I recorded the North American QSO party SSB at home. And I set the center frequency to 14,240 kilohertz and the sample rate to 96 kilosamples per second. And one of the syncs available in GNU Radio is a file sync. And so if I put in a file sync and tell it the name of a file, those samples will go into the file on disk, and it will record whatever you're streaming. So I have an open HPSDR radio, and I took the output of that and I sent it to a file sync, and I recorded for 15 minutes, and it produced a 670 megabyte file. So file sizes are not for the faint of heart when you're streaming at 96K. Then what we're going to do is the radio actually was programmed for 14,240 kilohertz. And so any signal that was exactly at 14,240 comes out of the block at 0 hertz. Something that's at 14,241 will come into the flow graph at 1 kilohertz. Something that's at 14,239 will come into the flow graph at -1 kilohertz. So it just takes the 96 kilohertz wide spectrum and drops it into 0, -48 to +48. So that's all built into the radio hardware and the GNU Radio block. Brings in those samples, and it looks exactly the same as a source. So a receiver in GNU Radio does exactly what a source does, produces samples, streams them in, but it comes from a real radio. What we've done in this particular exercise is let's open up the example. MUD exercises, exercise 4 SSB. So 4 SSB is a little more enhanced than 4, so let's bring in 4 SSB. And we have this flow graph, and this is a real usable receiver. Except that you don't need a radio, because I pre-recorded 96 kilohertz of spectrum into a disk file, and what this flow graph is going to do is read that out of a file. So we have this file source up here, and we're going to point it to go read the file that I previously recorded, put onto the USB stick, and you dragged over onto your desktop at the beginning of the exercise. So you have that 670 megabyte file now on your computer, and you can listen to the contest as it happened for those 15 minutes, and you can tune up and down. So what we do is we bring it out of the file, and we multiply it by this sine wave. And what this sine wave is it's tunable from -48 kilohertz to +48 kilohertz. And so what that does is it takes, let's say that there's a signal at 14,260. If we set this control to -20 kilohertz, the 14,260, which is at +20 kilohertz here, is going to get shifted in frequency by -20 down to audio. And so this signal source allows us to tune the receiver because it allows us to shift stuff that's way high down to 0 or stuff that's low up to 0. We're then going to run it through a low-pass filter, and the cutoff frequency is 1.5 kilohertz. Remember a low-pass filter with real taps goes from minus 1.5 to plus 1.5. So it's a 3 kilohertz wide low-pass filter. Now, we have to then slide that up by a little bit because we can't hear negative frequencies with our ears. And so we will slide the output of that signal up by 1.5 kilohertz so that negative 1.5 coming in here is 0 and plus 1.5 coming in here is 3. And if we change that frequency, we have passband tuning. We can now slide our low-pass filter up and down, and we implement a passband filter. Then we convert that to float, and we send it to an audio sync. So when we run this, we have to make sure that it can find the data file. So let's click on File Source here and open the file source. And it's going to ask us, okay, where is this file? And you'll see the 3-dot button here. Click the 3 dots and point it to where the file is on your computer. So there should be a MUD 2019, and you'll find this file 15 minutes, NAQP SSB 96K 14240. And that'll be in the folder that you installed. So go ahead and select that file, and then click Open. And now this block is going to go to that file to stream the samples. So we click OK. Okay, so double-click File Source. Click the little ellipsis, the 3 dots here. And it'll bring up an open menu asking you where it is that you want. Okay, so go into the folder on your, so go to Desktop. You'll see Desktop over here. Go to Desktop, then go to the folder that you dragged onto your desktop. And it'll be in there. It's called 15 MINS underscore NAQP. If it's not there, you may have to navigate down a folder to find it. Yeah. Okay. MUD. It's in the MUD class folder. And now when we run it, if we go over, sometimes the FFT will not start automatically. Both Linux and Windows have this problem. So go click the FFT button over here on your screen, right there, and pick any different value. And then it'll bring up the spectrum. So now this is the actual 96 kilohertz wide spectrum centered on 240 kilohertz that was recorded during the file. You may want to drag the averaging control over here to slow down the noise if you want. You probably want to take this passband control about halfway up, and what that will do is drag that low pass filter from -1.5 to +1.5 up to 0 to 3 so that you hear upper sideband. And if you drug it the other way, you'd hear lower sideband through that filter. Okay, this control right here, FFT, click the drop down and pick any other number. So you click this here. Okay. So does the trigger here say free trigger? Okay. So if we drag our passband tuning control up here, now we can use, we have a volume control at the top, and we have a tune slider here in the middle. Okay. Yeah, at 96 kilosamples per second, you're asking your computer to do a fair amount of work. And you'll notice that the frequency that is being displayed scrolls across the bottom at the same time. There's some other neat controls here. You can, for example, you can set max hold. And if you turn on max hold, you'll see it starts displaying the maximum signal that it's seen in the spectrum and records it. And if you're tired of that, you can just turn max hold back off. Pardon? Okay, let me take a look. Okay, click the FFT. This thing right here. There's your, okay.
While he's helping there, this is a real radio application with GNU
Go
Radio,
up to the 1024.
and you can see how you can apply it for your own
and
usage.
pick any other number, like
The,
2048.
The nice thing here too is that this is done with a flow graph that's on your memory stick, so it's an
no,
example.
it needs a new, it needs a change
And you
to
can
start.
find these flow graphs on the internet that other people have done. So if you're a little bit lost or this seems like it's hard, you can just get the flow graphs and start from there and modify them. And take this one, for example, and add to it or make changes to it. Just save a copy of it so you don't mess it up. But that's a very powerful part of this package that's going to continue to grow, because over time you're going to see more and more flow graphs available in more and more blocks over on the side that you can use to do various things. The things he's talking about on the right that you can do are all inherited by the block that he chose.
So the file source block is set up to loop, and you can change that and make it single once through. There's this control called repeat right here, and it says to yes. So every 15 minutes, it's going to replay that file. And of course, if you get tired, stop it and then restart it, and it'll go back to 0. No, you can't scroll through the file time-wise. And so the next step is to take this file source and replace it with a real radio. Literally, that's all we need to do to this flow graph, is to just get rid of the file and change it to the radio. Now, we don't have any HF radios that we can plug in right now, and so that's why we did the file demo, so you can play with the flow graph, you can play with the filters, the passband tuning, and you'll have a file where you can see what actually happens. And if you have a real radio, you can try that as well.
Since On that group of blocks over there, there is a block called RTL-SDR. So at home, if you have one of the little USB RTL SDRs, you could pick that and make that become your block, and you could use it as a radio.
So let's go through a couple of real radios here. So there's RTL, and we have RTL SDR source, so we'll grab that. And this block will go out and find your RTL SDR stick, which is plugged into the USB on the computer, and it will stream samples from it. And we've got a whole bunch of options, so many that we need a slider to get all of the options.
Documentation. You see all of those in that list there. Those are all the possible radios that this block supports. So you just copy the line that matches the radio you have, and you paste it in that top level where he was showing you, and you'll be operational with this block. This block is a very powerful block because it supports so many different kind of radios. Like Hack RF is down there in that list, and I think a standard RTL SDR 232 is in that list.
Yeah. Okay, so what we did is over here we searched for RTL, and it gave us RTL SDR source. So we double click that to drop it into our flow graph. Then we double click the block here. We'll double click, either single click and enter or double click. And that brings up the properties for that block. And some of the properties, for example, sample rate and channel 0 frequency. So this has the value 100 E6, 100 megahertz. So that will mean samples at exactly 100 megahertz will come out of the block at 0. And things a megahertz above will come out at +1. Things at 99 megahertz will come out at -1. And so this line is your tuning control. And if you want, you can wire that to a slider. And then you have the tuning control for that radio. It'll change what value it is. And you have a correction in case your RTL SDR stick has got a crystal that's off frequency. You can tell it how many ppm off it is, and it'll auto correct it for you automatically. Yes? I think it will go out and automatically find it. I'm not sure. I haven't used this one. Yes. Yes. The Osmocom source is the, so type Osmocom. There's a source and a sink. Yeah, the Osmocom driver is a multi-radio driver, and if the RTL SDR driver doesn't talk to your radio, try the Osmocom driver. It talks to 7, 8, 9 different radios. And the reason it's done is because if people write a radio driver that talks to Osmocom, then it will talk to GNU Radio. When you install the radio software for the radio that you buy, they have to have a Windows installer, and then you tell it, and the Osmocom source, I think, will search the USB interfaces to see if it can find one that's out there. Yes. It will also support the EDIS, although there's a separate EDIS driver built in as well. Now, we'll talk later about drivers. The GNU radio installs, the Windows installer installs drivers for about 5 or 6 different radios, but it doesn't install them for many more. And so I haven't played, since I don't own anything but a Netis radio, I haven't tried it to see how they work. But what happens when you plug in the Etis radio is it installs the driver loader, which is very non-intuitive. And then when you run it, it says, where's the driver? And you have to drill down into the C drive. The slide deck shows you how to find those towards the end of the slide deck. So let's examine that flow graph in a little more detail. So this GUI range I labeled tune, the ID tune, and I set the label value to tune. And what the label value does is when you run the flow graph, it'll label that slider and give it a name that you can see while you're running the flow graph. There's a second one called volume, and it does about what you'd think. The sample rate set at 96K. There's one called passband tune, and that slides the output of that plus or minus 1.5 kilohertz filter up or down so you can hear it. This is the signal source, which is the file. This is the tune oscillator. This is the low pass filter. It's plus or minus 1.5, which is 3 kilohertz wide. It's set to decimate by 2 and have a gain of 1,000. And the reason it decimates by 2 is because it goes into the audio sync running at 48K, but the file was sampled at 96K. And so we have to convert the sample rate from 96 down to 48. And so before we used a rational resampler, well, the decimation function is built into the standard low-pass filters. And so you can combine both the filtering and the decimation into a single block, so it'll save you having 2 blocks in your flow graph. And then we convert it to a float. And the multiply constant here, right now it's showing 1 because the volume control is default 1, but as you slide the volume, you'll change the multiply constant over in this block. So that gives you a volume control. The frequency sync here comes out of the multiply at 96K, goes through a multiplier to scale it, and that's the passband that you see on the screen. So a radio acts as a source, a receiver, or a sink, a transmitter. A receiver source can replace the file source in the previous exercise, or a signal source in the previous exercises. Different radios have different source and sink blocks. Different manufacturers code their software differently. Some blocks, like the OpenHT SDR block, is one block and it's got a sink input and a source output in one block. And other radios have a separate block for source and sink. So depending on how the manufacturer wrote the drivers, you may find it implemented one way or implemented the other way. A real radio tuning behavior will be slightly different than the file example. Why do you think that is? Well, in the file example, let's go ahead and run that again. We have a signal source that was pre-recorded from minus 48K, 0, plus 48. But when we run it, let's go flip the FFT number here. And let's tune it so that we take the stuff down at 14,196, which is down at the bottom of where we recorded it. And we'll slide We'll slide that up. And so now 14.196 got slid up to the center of the passband. We didn't record anything below 14.196. So where does all this stuff come from? It's circular. It's circular. The frequency that was 14.280 something slides over and becomes the frequency at the bottom. Right? Because a fast Fourier transform just looks at whatever's in there and it just wraps around either way. And so the file example is a little different in that you actually see this circular thing. If you have a real radio, you're actually going out and tuning the local oscillator in the radio and actually shifting the radio down and getting that real stuff from down there. So a real radio will behave slightly differently in that you can actually go below. But we didn't record that when we recorded the disk file, so there isn't any information down there. So that's why it's slightly different. So now, Bob, is it going to work? We don't know. We have a demo of a microwave SDR transceiver. So what we have on the computer here, this is an Edis B205, which is a 70 megahertz to 6 gigahertz SDR radio. It's the size of a credit card in a nice aluminum box. Its main purpose is to get the heat out of the parts. And it's connected to a couple of 2.4 gig antennas, one for the transmitter, one for the receiver. And it's powered off a USB cable. So the USB cable not only takes IQ samples to the radio and brings IQ samples back from the radio, but also provides DC power to the radio. So we're going to plug it in to a USB 3. And we can see we have light. And what does the flow graph do? Well, let's take a look at it. And they have a flow graph called B205 full duplex demo. The radio actually runs full duplex, so we've got a transmit and a receive antenna connector, and they're both going at the same time. So the radio is capable of full duplex operation. The block over here, USRP source. So that's our Edis B205 radio, and whatever's received, it streams into the flow graph. And we have the USRP sync, that's the transmitter. Samples from the flow graph get sent to the transmitter. And if we open up the receiver here, you can see we have a million options. We have mostly everything set to the default as it came. We have sample rate set to sample rate. And this one, the sample rate is set to, where is sample rate? 96K. Now, one of the things you'll find in radios is that some very inexpensive SDR radios can't run slow. They can run fast, but they can't run slow. So, for example, the Pluto radio has a minimum sample rate of about, 620 kilosamples per second. You can't run it any slower than that. And that means that in your flow graph, you have to take care to interpolate your data stream up to 620K. And then you have to send 620K over the USB interface to the Pluto. And so your poor computer is just beating its heart out trying to stream samples that fast. If the radio, yes. Okay, the question is, if you're streaming 620 kilosamples to and from the radio, and in your flow graph you convert it down to a slower rate, does it increase the resolution? And the answer is yes, it does. Decimation increases the dynamic range of the data stream coming in, and it does it for every time that you double or halve the data rate, you get 3 dB increase in the dynamic range. Now, if you're already at the maximum capable dynamic range of the A to D converter on the receiver, then you may not gain any more. And a lot of A to D converters, for example, you'll have an A to D converter who that outputs maybe 70 dB signal to noise ratio. If you decimate it, you may be able to get it down to 90 dB dynamic range, because the converter's dynamic range is actually better than its signal to noise ratio. It depends very much on the chips on the radio as to how much better you can get it. I found a number of 16-bit converters whose actual effective number of bits is more like 12. And so the A to D may be listed as a 16-bit converter, but its ENOB, its effective number of bits, may only be 12. And so its dynamic range is limited by 12 minus whatever you can gain from the decimation.
So let me add a couple of comments here. So what he's talking about is this block that he's got for his radio up there, which is from EDIS. And EDIS, are, the group of people at EDIS are the people that really put together GNU Radio. And they have some very nice radios, and he has one of the very nice radios that you can get. But in doing this work with GNU Radio, what you have to do is study that block carefully and understand the radio that you have, understand its capability internally. And usually the manufacturer documents it well, and it's typically based on the particular chip, the RF chip that's used in that radio. And in some cases there's onboard filters, for instance, and that's what limits the sampling rate that you can work with. So unfortunately, you just have to get to where you understand your radio. It's just like if you bought a Yaesu or an ICOM, you want to get certain performance out of it, you have to learn about that radio and how to get it to work the way you want it to.
That's a good point. So the benefit of adding more cost and more complexity to the radio is that it will have interpolation and decimation built into the hardware, and such that the rate that you have to stream over the USB cable can be a lot slower. And so it sounds contradictory, but typically the more expensive radios are capable of operating more slowly to the computer because they offload that interpolation and decimation out of the radio and implement it in hardware for you so that your computer can run slower, so that your interface doesn't have to stream samples so quickly to and from the radio. Exactly. They'll have a faster sample rate inside the radio. They'll have the filters. The Nyquist filters are programmable and built into the hardware inside the radio. And they'll do all of that for you. Yes. They have a very large FPGA, field programmable gate array, and it implements all the logic to do the interpolation, the decimation, and the filtering so that you can achieve a slow sample rate on the input. And secondly, they have a very high performance RF chip. So the chip in here goes to 6 gigahertz and is capable of operating at an output rate at 6 gigahertz. So the receiver will run 6. So this radio will run 70 megs to 6 gigs. So the cost is involved in the chips that are capable of implementing all of that hardware. So is that a lot? I don't know. If you get, you might have to replace that with 5 radios, right? So it's continuous from 70 megs to 6 gig. So there's a lot of capability in there for that price. So It is. The Pluto has a similar RF chip, but it's missing a lot of the digital signal processing functionality that this particular one has. So, so it's a cost performance trade-off, right? Which one do you need? This particular one also has very rapid TR switching and can be used for burst mode. There's a lot of other features. Is it worth the additional cost? Well, that's what you have to decide. Do you need it for your application? Yes, it does. Yeah, I don't think the Pluto is supported on Windows yet. It is supported on Linux.
Let me say that that's correct. It isn't supported here yet, but I think that in time you will find that it is, and you'll find other devices like these coming out. But the advantage is to the GNU radio, if you can get a Linux system up and running, once you open GNU radio, it's the same as it is in Windows. The blocks over on the side will change, the available blocks. And I think you will always find more blocks available in Linux. And it's because Linux is an open hardware solution where Windows is proprietary.
Yeah, the build process on Linux uses standard tools. And so it can be done fairly easily by someone who's not real familiar with the details of GNU Radio. That process is quite difficult on Windows. And so the maintainer built the Windows package that we installed today. He had to go resolve all of those Windows specific build issues. Yes. Okay. Okay.
Let me say that we're running a little bit short on time, and we have a lot of stuff we were going to tell you about. One of our thoughts is we're going to go to lunch or dinner, and if you wanted to come back here and experiment more or learn more, we can do that in this room later. But part of the idea of the demos too were to try to demonstrate some things that can be done with microwave, and so we were trying to push this up into the higher frequency, and that's why we're trying to do this at 2.4 gig, okay?
Right. So if one of the tabs on the Edis radio is RF options, and we program this line channel 0 center frequency, and we put in the word coarse frequency, which is one of our sliders. And so that will tune the radio to whatever we put in the coarse frequency function. And the general function we left at all the defaults, but we also had to set the sample rate, and we used the sample rate variable that we previously defined. And there's a couple of other features that the radio has. So the receiver goes through a multiplier selected by the signal source, and the signal source is set to tune about plus or minus, I call this one fine frequency. And so it tunes from, where's fine frequency? It tunes from minus 100 kilohertz to plus 100 kilohertz. So it lets us fine tune in the channel. And the reason for that is the crystal oscillator in here might not be dead on frequency. In fact, I can pretty much guarantee it's not. And so we have a course to kind of compensate for that. And then another slider called very fine frequency, a slider called receive volume. And so we multiply the receive signal, we low pass filter and multiply the receive signal and send it to a sink. On the transmitter, the audio source, which is the microphone on our computer, is the input. And we also have a tone that we can transmit in case we get tired of yelling hello test into the computer microphone. It will add those two. And then we have this special filter called Hilbert. And what Hilbert does is it lets us take this signal, which is a float. Remember, that's a double-sided spectrum signal. And it will automatically create a single-sided signal from it. So this will generate an upper sideband only audio signal. And we run that audio signal through a low-pass filter into multiply, which again lets us translate the frequency into the sink. So full duplex, the receiver, we listen to it and we produce the output in the audio sink, And whatever we say into the mic gets transmitted as an upper sideband signal into the transmitter. So this is an entire single sideband transceiver flow graph for a radio. And that's about how many blocks it takes.
Okay, so I took his blocks, just like he's got there, and I implemented the very same thing with the Pluto. So I just took away the Edis block and put the Pluto block in its place. This happens to be running on Linux. I had to put in rational translators to change the rates because of the sample rate. But so we're implementing the same block in both places. And the tone he mentioned is so you can aim your dish if you're roving to get lined up if you're using this as your baseband, for instance, with a transverter.
Okay. So we're going to start this up, and this will take a little bit of time. This particular Edis radio does not back up the contents of the FPGA, and so since I just plugged it in and powered it up, the first time it has to download all of the radio-specific digital processing code into the radio. It's not the processing code from this flow graph, it's the Edis driver that it downloads into the radio. Yes, this third connector with the cap on it is a 10 megahertz input signal, and if you go into that block, you'll find an option to select an external 10 megahertz reference to lock it. So here is the flow graph running, and I have course frequency defaulted to 2304.1, so it's on 2.3401 gigahertz, and that's that block in the radio. We have the very fine frequency, the fine frequency, and we can see now we're actually displaying the spectrum that the receiver is seeing on this antenna from a frequency of about 2304.55 up to about 2304.150. And so this is actually operating as a spectrum analyzer in real time on this antenna for that receiver. And if we can get everything to work and they transmit their test tone, we'll actually see the test tone pop up in the middle of the spectrum. And it wasn't working as of about 1:30. So there we go. Okay, so they're transmitting the 1 kilohertz test tone, and we're from that antenna right there, and we're receiving it here, and you can see it. You can see it on the spectrum analyzer, and they just turned it off. So now I can turn on my transmitter. So I implemented a block here called transmit, and what that will do. Remember, the radio is running full duplex. What it does, when the transmit block is off, it multiplies the sound from the sound card by 0. And that effectively mutes the audio from the sound card. And it sets the audio from the receiver multiplied by 1. And when I check it, it multiplies the transmit audio stream by 1 and the receive audio stream by 0. So what it does is eventually it's push to talk, mutes the receiver and enables the transmitter audio, and when it's deselected, it enables the receiver audio and mutes the transmit audio. So I achieve half duplex just by checking this block on and off. And all it does is it's a variable, and the multipliers look, and if it's enabled, then they multiply by 1. If it's disabled, they multiply by 0. So it's as simple as that. So we'll click transmit, and we'll turn on the tone. And because we're full duplex here, you can see we're seeing our own receiver, and we're seeing the 1 kilohertz tone that we're sending mixed in with whatever the microphone is picking up on this laptop. And so if I turn off the tone here, you'll see that tone disappear there. And now you can see this is the actual 3 kilohertz wide audio that's been converted to upper sideband that we're seeing in the receiver. And are you seeing that on your spectrum over there?
He turned it off, I think.
Okay. Whistle. There you can see my... sort of a tone coming out. And because it's upper sideband, you just hear the single tone for it.
Okay, let me mention that I've had all this stuff working at home just fine, but when you bring it here, it doesn't work exactly the same. I've also, my experience has been that I've had everything working, and when I go out roving, it doesn't work the same. You start blowing fuses and doing all kinds of stuff, right? So, but we've seen it. It's working now, so you could whistle over there, and we'll see if we see you, Tom.
Okay, let me transmit.
Yeah.
Okay, transmit level.
Yeah, okay, so there he is. Okay, so somebody talked about being on frequency or not. I'm sort of a proponent of the fact that you have SDR here with a waterfall, and if you want to be a rover, for instance, don't worry too much about your frequency. Just get close and go out there and let that guy that's in his shack or something get better frequency control and look for him. On the other hand, if you really want to do it, you can do GPS, lock your signals to it, and really have good control. So you can see that in this case, we're hooked to this Pluto with a USB cable, but we could service this with an Ethernet port. And the beauty of that is you could locate this back out by a dish and bring it into the cab of your truck or whatever, or into your shack so that you don't have to have all these feed lines. The tricky part could be temperature control, whether or not you have real hot weather, things like that, just packaging it up properly. Yeah. But it's a beautiful way to do some microwave work, I think, for a baseband remotely connected to your computer or to your transmission.
So if I type 1296.1 in here, without changing anything, we have a 1296 megahertz radio. And I've tested that at home with a friend who's got a 1296 single sideband radio, and it works fine. And because this radio will go up to 6 gigahertz, just by changing what we type into this block here, we change what band we're on, and we essentially have a 9-band transceiver just by the number we type in there. We can put this on 9 different ham bands from 6 meter, well, won't quite go to 6, so 2 meters, 220, 432, 900 meg, 1296, 2 gig, 3 gig, 5 gig. We can put it on any of those bands just by the number we type into the block. So we have 9, maybe it's 7, I can't count, band radio here. Now this radio does not have RF filtering. And so for any practical application, we're going to have to put an appropriate filter in the antenna leads. Otherwise, we're going to make a nuisance of ourselves on transmit, and our receiver will be overloaded. One of the Edis radios in the 300 series is a much more expensive radio, but it's got all those filters built in. And as you type the different numbers, it will automatically select the appropriate RF filter and automatically switch in and out. But for that convenience comes a very large price tag. So it's the trade-off that you have to do. Yeah. Right, right. You'd need a way to tell that filter what band you want to select it on. Yes, sir. This particular implementation buffers about 50,000 samples, and so at 96K, it's on the order of 1 second latency. If I run it at a faster sample rate, if I double the sample rate, the latency halves, but then I have to make the computer work twice as hard.
And that also depends on your filtering and what you do in the radio blocks, that latency.
Carl?
Yeah.
Yeah, we flipped them. So this one, the T and the R are flipped compared to that one. Yeah. There's a vertical antenna here and there's a horizontal. And I'd pick it up and show you, except it'll rip something out of the wall if I do it.
Question.
Yeah, it's the same exact antenna as this one over here.
Okay, what's your question?
One more. Okay. Yes. Okay. Yes. No, no. So the question is there some utility that goes and finds where every instant of this block is used throughout a flow graph? No, there's not. So you just have to manually go check it. There is a quick and easy way to do what you ask. If I go up to this block and I change the name of it, okay, now all of a sudden this block turns red because it can't find PTT, and that block turns red because it can't find PTT. So it sort of does that function. And so if I go back up to here and I fix it, now they all go back to black. So that's one way to kind of do that.
Okay, let me mention that Tom still has a few more slides left that we'll probably have to cover later. I want to mention one other thing to you that I worked on, that, and with Tom's help too, that I did that I'm really kind of excited about or feel good about. And that is, if you take these blocks and you take that file block, you can make yourself a file block. And the way I did it, I built a SSB radio so that I was copying SSB, and I did a recording of a file. And what I did was I made a beacon. So I created a file that just said N5BRG beacon. All right, and then after I had that file and I set it on replay, I've got it in the Pluto, and now it'll just sit there and play over and over again on whatever frequency I tell it I want it to be on for my beacon. So I've made a very simple beacon that would work up to 6 gig, or with a mixer I could take it up to 10 gig. And I have one of Paul Wade's mixers here. I could feed the Pluto into this. This is a 9X device, put a filter, a 10 gig filter out here, and bam, I'm on the air with just a maybe $250 or so. I've got a 10 gig beacon, or whatever band I want it to be on. And we have that working here, and we were going to play it, but I don't think we have time to do that right now, but we can do it later. There's a little flow chart.
So here's a block diagram of what Bob was saying, a beacon where you take a single board computer, perhaps running an SD card, and you burn the audio file that you want to send along with GNU radio and the single board computer's operating system onto the SD card.
In the audio file, you could also put CW in it, and you could also put FT8 or some other digital mode. And that was the other thing I wanted to mention. If you're really into microwave and maybe you want to go out and make some records for distance communication, the best way to communicate is with digital modes, because you can use forward error correction and you can get more dB for your range. Plus you can use other modulation techniques. So to employ some of this GNU radio stuff, if you wanted to try to set distance records, I think this is the way to go.
Right. So in this case, you'd have a radio, some kind of a broadband amplifier, and then probably a selector filter bank. So you could then build a beacon that would step band by band. And it's probably a multi-band, multi-microwave band beacon implemented like that is probably fairly small and low power, and may, depending on the cost of the radio, may be cost effective. So it's just sort of a, kind of an example of what you could do with GNU radio. Yes.
It still strikes me that this isn't a useful radio, but if I'm out in the microwave browser, I'm trying to find somebody who's not quite on frequency and trying to tune them in.
Yes.
If they're talking SSB, I have to tune the dial, wait a second to see what I'm going to hear, then tune the dial again and wait another second. It's going to take way too long to get tuned in.
That's if you run the sample rate slow at 96K samples per second, for example, with this particular radio.
Come down to anything more than 30 to 50 milliseconds, it's going to be too long.
Yes, this particular one has a very large FIFO buffer on the transmit of 50,000 samples, and there are other radios that have much smaller buffers. If they have a smaller buffer, they'll have a lot less latency. That sounds like a good question to have after the session.
And I think with if you're putting out tones on both sides looking for each other, you're going to spot each other, and then you can do the tuning later.
Okay, to wrap up here, help. GNU Radio installs help on your PC. This slide's in your book, so you don't need to write anything down. Here's the URL that got installed on your computer when you installed GNU Radio, and it's the manual, tells you about all the blocks, and it's written in GNU Radio software ease, so you may not find it the most friendly help, but it's sort of help. Examples. There are a number of examples that were installed along with GNU Radio on your computer, so you have the examples that the GNU Radio folks installed right on your computer. There is a main page, wiki.gnuradio.org, and go to the GNU Radio website. There are a number of tutorials for GNU Radio. wiki.gnuradio.org/index/tutorials. Go to the tutorials. They're really excellent, and they will take you step by step through many of the other processing blocks and many of the other functions and features. And I've gone through this tutorial. They're really very well done. GNU Radio mailing list, which is very busy. It averages probably 2 to 3 dozen postings a day. So you may want to subscribe to it in digest mode, where you get 1 or 2 emails a day, each of which contains a dozen or 2 dozen topics. The EDIS mailing list for EDIS radios only, which is busy but not very busy, and you can find that at this URL. Pluto, I'm sure, has its own mailing list, so whatever radio you have, get on their mail list. And if you have a question, you need help, if it's a GNU Radio question, go to the GNU Radio mail list and post your question, or look back in the archives. Someone else has probably asked your question before. Or if it's particular to your radio, go to your radio mail list and look through the archives, and if you can't find the answer, post a question. Friendly folks, they'll help you out, they'll help answer your question and get going. There's lots of good support on the mail lists. And the drivers, every radio is kind of different. And so you'll need to, if you get stuck on your particular radio, go to the mailing list, and people will help you get your radio drivers going and installed. And with that, I think we've hit time. Any other questions? Bob, any other final comments?